Hello everyone, I'm Mulong, a PhD student from Cornell University. Today I'm going to talk about cache side channel attacks in autonomous vehicles. Since autonomous vehicles are reaching our everyday life, the privacy issues raises more concern. Even though we will focus on autonomous vehicles, this work is broadly motivated by privacy issues in the cyber-physical systems, including autonomous vehicles and UAVs. One thing particular about cyber-physical systems compared to other computer systems is that the privacy in the cyber-physical systems involves in physical information, such as locations. On the other hand, cyber-physical systems as computer systems are also vulnerable to cache side channel attack. With the privacy issues of cyber-physical system in mind, we have made the following contributions. First, as mentioned, we identify the physical privacy issues in the cyber-physical systems, unlike privacy issues that usually leaks non-physical information such as crypto keys. Second, we identify a specific categories of algorithm, that is, adaptive algorithm, whose computations are input dependent that are vulnerable to cache side channel attack. Third, we show that one concrete example of the attack, that is predicting the route of autonomous vehicle using the cache side channel attack. Since this work is about an attack, let's see the threat model. Here we show a map of the world with road and different locations. The vehicle runs around and we want to predict the route of the vehicle from a set of known routes. We assume the attack software and the victim software runs on the same computer. The attack software should not be able to access location services such as GPS. The way we get the physical information is through the cache side channel. In the example slides, there are three potential routes that the victim vehicle may take from home, depending on its destination. The attacker's goal is to infer the route among three candidate routes. The example shows the case when the vehicle takes a route to the airport. Since our attack focuses on the computer system of autonomous vehicles, let's take a closer look at a typical platform. Main components are sensors, actuators, and the computer. Multiple software regarding the autonomous driving systems run on the computer. This includes estimation and localization software, as well as the control and the decision software. We attack the localization software in this work. Let's see how the attack works. There are three major steps. First, adaptive Monte-Carlo localization is a victim program and runs on the victim's vehicle. Its memory access patterns will be affected by the physical sensor inputs. Next, cache side channel attack is performed to extract memory patterns. Third, machine learning models are used to predict the number of samples in the AMCL and the route of the vehicle. Let's start from the adaptive Monte-Carlo localization. Adaptive Monte-Carlo localization is an localization algorithm used in many autonomous vehicles, especially those with LiDARs. The inputs include sensor readings and a map. The gray regions are obstacles while the white space are the free space. So in the map, we show a T-junction. The output is just the location on the map. At high level, it works like this. First, location is randomly selected on the map, and for each location, we calculate the similarity between the sampled location and the sensor image. Second, the cluster center of this sampled location is found using k-means. The cluster center is the output of this algorithm. The adaptivity lies in that the number of samples varies adaptively, depending on the uncertainty about the environment. Empirically, there are more uncertainty when the vehicle is turning. Thus, as shown in this figure, the number of samples in blue line and the trajectory curvature in orange line as a function of time are correlated. With more samples, there will be more memory accesses, which can be inferred by the cache side channel attack. Let's see how we use the cache side channel attack in our work. We assume that the cache is shared by the AMCL and the attack program. Due to the cache sharing, the access patterns of AMCL are left in the cache, and the attack program can extract that pattern by timing its own memory access time. In this work, we use the Prime+Probe approach to extract the pattern. Other cache time channel attacks may also be usable. For the Prime+Probe attack, for each trial, we probe each cache set and record the probing time. The result is this 2D matrix in which the x-axis is the Prime+Probe trial index, while the y-axis is the cache set index, and the color indicates the cache probing time. Essentially, high probing time indicates that the particular cache set is accessed by the victim. In general, more dark cells means more samples in the AMCL. And we can use a machine learning model to predict the number of samples from the cache probing time. Let's see the model. Empirically, we observe that the number of samples in AMCL are either maximum or minimum. Thus, instead of predicting the exact numbers, it is formulated as a binary classification problem. The cache probing time matrix from Prime+Probe is put here, and we use it as the input. The output is one of two classes, high and low, representing the number of samples. And we use Rashboost predictor for this prediction. By moving the sliding window, we get a series of high and low, and we can use it to predict the route of the vehicle. Here comes the route predictor, which takes in a series of high and low representing the number of samples. And the output is pretty simple. It's just the label of the route. We can use a decision tree or forest for this prediction. For example, given this tree, by checking the high and low at each segment, we will be able to know that the vehicle is on Route 8 in this case. Thus, we finally be able to find the route of the vehicle all the way down from the memory access patterns of AMCL. Let's see how this attack works in evaluation. Two datasets are used in the evaluation. First, we use a dataset generated by Gazebo raw simulator, which are used by many startups to develop autonomous vehicles. Here we show a maze simulated by the Gazebo, and we perform experiment in this maze. Second, we use data collected by a car in the UK town of Oxford. Here we show the map we used in the Oxford dataset. For the hardware, we use a Intel Xeon processor recommended by the Apollo autonomous driving platform. We've also used a low-power Intel i5 processor. Let's see some numbers. First, in the Gazebo dataset, we chose 7 different routes with similar lengths in the maze. And here we show the prediction results of these routes based on level 1 data cache and the last level cache attacks. The x-axis is the ground truth label of the routes, while the y-axis is a predicted label. Most of them fall onto the diagonal. The accuracy are 81.4% and 75% for L1D and last level cache. We've also done similar experiments in Oxford dataset, and we show the prediction results here. Notice the accuracy is lower in the Oxford dataset. This is due to the fact that the noise level in the Oxford dataset includes both noise from the physical world as well as noise from inside the computer. Still, we get a reasonable accuracy for the prediction with limited amount of data. We've also discussed following issues in the paper with the pointers to the corresponding sections. For example, the paper provides more details in testbed and the experiment results, show that the route prediction can be used to predict the destination location, and compare and discuss the generality and the limitations of the proposed attack. In summary, we address the privacy issues in the cyber-physical systems and autonomous vehicles, and showed in particular that adaptive algorithms are vulnerable. And we demonstrate an example that extracts the physical privacy information in adaptive algorithm using cache side channel attack. For strong location privacy, cyber physical system software and hardware designers need to carefully consider and prevent information leaks through cache side channels. And thanks for listening.